Hello and welcome to this video for our last section here in Unit 6. Today we're going to talk about Hess's Law, which is really going to be a lot of addition. So with Hess's Law, we are going to be taking a couple of things into account. Okay, so a few concepts that we've learned over the last 2 units. So number one is that a chemical reaction is going to be made up of one or more elementary steps. And sometimes a chemical reaction can be represented as one series of steps or as a different series of steps if perhaps we introduce something like a catalyst. Okay, so with that, and each step for a reaction being itself a reaction, each of those elementary steps is going to have an overall enthalpy change for that reaction. All right, so we know that from kinetics that each of those elementary steps need to add up to become the overall reaction. Well, if each of those steps have a enthalpy for reaction, we can add those up too, and those are going to equal, when we add them up, the overall enthalpy of reaction of that reaction, okay, that the elementary steps add up to become. So what Hess's law is getting at is that, again, we could have several different pathways to get from our reactants to the products, okay? But no matter which pathway we take, we are still going to have the same enthalpy change. And we know that from reviewing the energy diagrams when we have a catalyst. All that does is change the activation energy, but it doesn't change where we start and where we end. Okay, so again, enthalpy is a state function. It will start, a reaction is going to start at a certain energy level and it's going to end at a certain energy level. So the change in enthalpy is going to remain the same regardless of the pathway that it takes to get from reactants to products. Okay, so the quote that I have down here, is very useful for helping you out here. So in going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether a reaction takes place in one step or in a series of steps. Okay, so it doesn't matter what these steps are, as long as we are starting with the same reactants and ending with the same products, it doesn't matter what this series of steps is, we are still going to have the same change in enthalpy for that reaction. Okay, so let's kind of take a look at what we mean here. So the production of nitrogen dioxide, which we have here, so N2 plus 2O2 yields 2NO2, has an overall enthalpy change of 68 kilojoules. So this is positive. That should tell us that it is endothermic, so it requires energy. It requires an input of energy. But this reaction, this being the overall reaction, occurs in 2 steps. So we have step 1 and we have step 2. So N2 plus O2 yields 2NO. 2NO plus O2 yields 2NO2. Each of these steps has its own change in enthalpy. Okay, so this one for step 1 is 180 kilojoules. This one for step 2 is negative 112 kilojoules. Okay, so we have 2 different reactions here. One being positive, endothermic, and the other negative, exothermic. So let's make this look a little bit more like an addition problem. So we're going to put the 2 elementary steps that we're adding together up here so that we can see this a little bit more easily. So step 1, step 2, the delta H for this step, delta H for this step. Okay, so When we add these two reactions together, we get our overall reaction. So N2, 2NO, 2O2, and then 2NO2. This 2NO and this 2NO, they cancel out. Okay, so these two steps add together to get our overall reaction. And you'll notice that the H2 here oriented in this way, 180 kilojoules. The H2 for this step oriented in this way is negative 112. They're oriented correctly. They have the proper coefficients. So when we add them together, we get our overall reaction. And when we add these two together, we end up having the same change in enthalpy of our overall reaction. 180 plus negative 112 is going to give us 68 kilojoules. Okay, so the sum of our two steps here gets us the change in enthalpy of our overall reaction. Okay, so we do that with the reactions. We do that with the change in enthalpy. It works the same exact way. Okay. Sometimes we might have 3, we might have 4 reactions. It would work the same way. All of those steps, regardless of how many they are, they add up together to get our overall reaction. And we would add up all of the change in enthalpies for all the steps that we have to get the overall change in enthalpy. Okay, so sometimes it's not going to be quite as easy as what we have back here. These were already oriented the right way. N2 plus O2 yields 2NO. 2NO plus O2 yields 2NO2. They're already oriented the right way. That is not always going to be the case. Okay, so sometimes we might have to reverse a reaction. And you should recall from earlier in this unit that if you reverse a reaction, then you have to change the sign of the delta H value. Okay, so going back here, if we were to reverse this and have 2NO yields N2 plus O2, well, we're reversing that reaction. We have to get the opposite sign here. So that would have a delta H of negative 180 kilojoules. Okay, so if you reverse a reaction, you have to change the sign of the delta H. Likewise, if you need to multiply your reaction by an integer or even a fraction maybe, you will have to multiply your delta H by that same number. Okay, so if we multiply by 2, you would have to change delta H by multiplying it by 2 as well. So you only change the sign when you reverse it, and you'll only multiply your delta H by a number if you multiply the reaction by that number. Okay, so going back here, if I were to take this one here and multiply this by 2, so I'd have 2N2 plus 2O2 yields 4NO. Well, now we have double of what we had before. 2 moles of N2, 2 moles of O2, 4 moles of NO. Well, it's going to take twice as much energy to do that. So that's going to give us 2 times 180 or 360 kilojoules. Okay, so let's look at these examples here. So if I have a reaction Xe plus 2F2 yields XeF4, and the delta H of that is negative 251 kilojoules, well, what will I have if I manipulate the reaction in several different ways? So let's take a look at this one. XeF4 yields Xe plus 2F2. So why don't you pause the video and try to figure out what the delta H will be. Okay, so the reaction, you'll notice, we reversed it. That's all we did. So we took the XeF4, put it over here. We took our reactants, put them over there. Xe, 2F2. We did not multiply the coefficients by anything. Therefore, since we reversed it, didn't multiply by anything, all we have to do is change the sign. So we would have negative 251 normally. If we reverse it, then we change the sign. It's going to be positive 251 kilojoules. Okay, now what about this one down here? Now we have 3xe plus 6f2 yields 3xef4. Well, we haven't reversed it. Okay, we still have the reactants, same products. However, you'll notice that we multiplied everything by 3. 3xe. 3 times 2, so 6f2, and then 3xef4. So we did not reverse it, so we don't change the sign, but we multiplied this by 3, so we have to multiply this by 3 as well. So negative 251 kilojoules times 3, it's going to get us negative 753 kilojoules. Okay, so hopefully that made this clear enough. Now, let's take a look at the example that we looked at before. So our first step, second step for the N2 plus 2O2 yielding to NO2. So if we put this in a little schematic here, we can look at it in terms of those steps. So delta H2, 180 kilojoules, that's our first step. Well, that is going to require energy, so we're putting energy in. So that's going to give us an arrow up. Delta H3, negative 112 kilojoules. Well, that's going to bring us back down because it's negative, so we go down. However, this number is not as big as this, so we're not going all the way back down to where we were before. Okay, so first step, second step, notice that there is a difference here between the two. So if you've been following along, the difference in this case is going to represent the overall delta H of our reaction, okay? So we go up 180, we go down negative 112. So overall, when we add those two together, we end up with the difference, which is 68 kilojoules, okay? So this is the overall reaction, delta H for the reaction, which is going to be delta H2 plus delta H3, and we just put those together and we end up with 68 kilojoules. All right, so to finish this up, I want you to try out these two practice problems. So the first one, 2 forms of carbon are graphite and diamond. Using the enthalpies of combustion of graphite, negative 394 kilojoules per mole, and diamond, negative 396 kilojoules per mole. Calculate delta H for the conversion of graphite to diamond. So why don't you go ahead and pause and try this out on your own. All right. So I'm going to go ahead and go to the next practice problem. So the next one, this is going to be a little bit more complicated. So diborane B2H6 is a highly reactive boron hydride that was once considered as a possible rocket fuel for the US space program. Calculate delta H for the synthesis of diborane and from its elements according to the equation 2B plus 3H2 yields B2H6. Well, we have 4 steps here. So your goal is to figure out how we can add these up together to get this. You may need to reverse some of these. You may need to multiply a few of them by an integer. Okay, so try to figure that out on your own. You can pause the video here to do that. All right, so our very last page here in this section involves just some tips for problem solving with Hess's law. So hopefully you're already doing this with the 2 practice problems, but what you want to do is work backward from the required reaction. Okay, so look at what the reactants and the products are and use that to determine how you need the reactants, the reactions, the steps oriented, like if you need to reverse them or not. Use that to figure out if you need to multiply any of them by an integer too, okay? So reverse any reactions that you need in order to get the correct reactants and products, multiplied by an integer to give the correct number of reactants and products. And I'll be honest, sometimes you might just need a little bit of trial and error in order to get to the right spot.